Hello, my name is William Rose. Today we'll be doing the effects of heat on batteries, and this is part of the chemistry in the real world project. Um, Today we'll be looking at the effects of heat, both high temperature range and low temperature range. We'll look at a couple different battery types and how heat affects them. And we'll also follow up with some of the options as far as mitigating heat or reducing the temperature range and in order to increase the efficiency and the longevity of batteries in general. Here I provide an overview of what we'll be covering today. We'll start off with the module connections, why I selected the topic, the real world connections, some commonly used terms, and then we'll actually start getting in and dissecting the batteries, different types, chemical makeups. Um, I look at a couple couple different batteries and do a comparison, and then we get into discharge curves, the temperature effects, both the effects of heating and cooling, and ways to maintain the batteries, and then we'll follow with references that I use within the project. For this slide, I look at some of the module connections. Um, I specifically chose module learning objectives 1 through 8. Those are pretty generic objectives. They include distinguishing between elements, compounds, mixtures, integrating knowledge of quantum numbers, atomic orbitals, electron configurations, using the periodic table, applying our knowledge of attractions to predict the effects of matter, drawing appropriate Lewis structure for molecular and polyatomic ions, also performing calculations and identifying reactions. Specifically, there is a section in the textbook that relates to this pretty heavily. It's in chapter 18. It's the electrochemistry looking the quest for clean energy, which this topic with batteries and alternate power solutions directly relates to that. So here I wanted to provide a reason for why I chose this topic. So I wanted to provide a personal connection between items that people live with on a daily basis and that they may rely on and establish a personal connection. So the way I present it, I try to take the material and I try to present it in a way that's easily understood or understandable for people and make the connections between what they might see every day and then provide kind of some of the more in-depth chemistry related elements of that, why it reacts the way it does, why the life of it is the way that it is. Also in a different condition, if something's in your house versus something's outside or in your garage, it might react differently. It can come down to a car battery, even if you have, a 24 series battery and it's in your car and you live in North Dakota, it's going to react so significantly different than if you live in Texas. Or maybe you're moving after school, or you're getting a different station. You're in the military, and you were stationed in Florida, and now you're getting stationed in Alaska. Everything's going to react differently, and hopefully the way that I present this, you're able to make that connection. You're able to utilize what you've learned in this class, and then kind of relate everything to itself, and it's not going to catch you off guard. So into the second bullet point here, um, the environmental parameters play a large role in the chemical reactions internal to the batteries. Um, so I try to help provide enough information to where you can look at kind of a balancing method between heating and cooling. You could maybe mitigate the environmental effects, um, and then it will ultimately last longer. It'll result in a longer lasting, more efficient battery or alternative powers solution. Um, there is a higher dependency on the resources that are required to make some of these elements, or well, the elements are scarce. And in order to provide the alternate power solution, those materials are becoming more scarce. With that, you have increased cost. You might have increased lead times, and then also just getting everything available. It's going to become more scarce, I believe. And if you're able to mitigate some of those risks and the result is a longer lasting power solution, it's only going to be more beneficial to you, last longer, to be cheaper, and I think that'll be helpful to the community. As far as my real world connections, in my professional occupation, I've had an increase in the dependency of batteries, specifically just alternate power sources. So whether it's a battery working in conjunction with a generator or solar panels working in conjunction with batteries. Um, 2 years ago, I never had a request, and this past year alone, it seems like my entire occupation has revolved around this specific topic. So professionally, I have had that increased interest, and now it's related into things that are kind of like government contracts or military contract related. And so you have kind of mission critical components that are being implemented in extreme temperature climates, cold or hot temperature climates. Um, and so having a better understanding of the composition of each individual battery and its type helps me basically achieve that mission critical component. Um, and then also mitigate risk. If you have something that is mission critical, obviously you have to have a redundancy and you have to have a pretty in-depth level of understanding with the internal composition and how long it's going to last. Some of the criteria I get, you might need to be completely off grid for 6 to 7 months with your alternate power sources, and you can't really have something that is mission critical fail, and especially when it has such a high dependency, whether it's with communication um, or just some sort of life providing service. It's just not an option. So I also attended a symposium fairly recently. It was probably 5 or 6 months back, but it was specifically focused on batteries and battery powered systems with the focus on heavy equipment. It was tractors, tanks, drones, refueling systems, which are 100% battery powered, but with alternate power sources. So the main focus actually was on using used or previously used batteries in conjunction, taking their depreciated values, combining them in a way or modifying them in a way to where they could be utilized for these heavy equipment pieces. And so there was a lot of interest there, and that was also another reason that I took and chose this as a topic. Throughout this project, I'll be using a lot of commonly used terms or maybe terms that not everybody is familiar with. So I wanted to provide one slide that kind of captured my commonly used terms. These are not a textbook definition or a dictionary definition by any means. I tried to provide them um, based on a way that I understand them and that they're used kind of in industry um, in conjunction with the textbook definition, but I didn't want to overcomplicate or go too in depth on any one specific topic. So for some reason, if you're looking at this or you're reviewing this and you have questions or anything, just let me know. But you can always refer back to this. I do have some notes later on in the presentation that say, refer to this for like a conflicting item. So when we get into how lithium ion battery, or not lithium, sorry, when we get into how sealed lead acid or just lead acid batteries work, we talk about one of the issues with a lead acid configuration. And one of the, let's see, effects of the chemical reaction is the risk of sulfation. So I have a note in there that says, refer to sulfation for conflicting action item. And so I'll point that out later when we get to it, but we can always refer to this commonly used terms page later on. So now I'll actually get into kind of the meat and potatoes of how the batteries work. So for this project, I really looked at two main different types of batteries. There's a million different chemical compositions that we could look at, but I try to use two that are fairly common. So lead acid and lithium ion. So how they actually work, if we look at just lead acid, you have an electrical charge that's generated. So you have sulfuric acid within the lead acid battery, and the electrical charge is going to be generated from the sulfate within sulfuric acid becoming bonded to lead. And so that is how it is generated. On the opposite end, once there is no sulfate that can be bonded to the lead, the battery is considered in a discharged state. And that formula leads to lead sulfate. So I do have the formulas there for it, but really what you need to know is that once we get to a discharge state, we can recharge the battery, and that reversing cycle will have the sulfate reattach into sulfuric acid. So basically, it'll get removed from the lead, it'll be reattached to sulfuric acid, and then we will have the porous kind of lead that can now be reutilized and have that same cycle where the sulfate from sulfuric acid becomes bonded again to lead, which will result in basically you having power availability, and then we just continue to reverse the cycles. So I do have a note there with the asterisk at the bottom. There's a limitation by the ions in sulfuric acid and the surface area of lead. So I have that note that says see sulfation for conflicting issues. Um, so really what you need to know is that once there is no more ions in the sulfuric acid or the surface area that is available, basically you have less capacity. So the sulfation, that ends up happening when you have a crystallization form, and it would basically be like adhered to that lead plate. And so you end up getting a reduced capacity because your surface area is being reduced. And that sulfation can be caused by not allowing the battery to get to that full charge cycle. So if you do incremental charges, basically you can have a crystallization form, which ultimately will result in a reduced capacity. There are ways to mitigate that and to decrystallize that sulfation, which once we get to later on in the PowerPoint, I'll highlight some of those areas. But that's in general how the lead acid battery works. I do have another slide that's coming up next where I give another picture and annotation and then kind of provide a little bit more of a visual to help that understanding. So we'll switch gears. We'll go to the lithium ion. And so with the lithium ion battery, the chemical composition is totally different. The structural buildup is completely different. But basically, you have an electrical charge that's generated by positive charged lithium ions being carried by an electrolyte, and it's being carried through what they call a separator between the anode and cathode, and then vice versa. So positive charged lithium ions transferred between the anode and cathode, and that's creating your electrical charge. So with the movement results in free electrons in the anode, which creates a positive charge at the positive collector. You can imagine kind of the positive terminal. So then the current will flow into the device being powered, whether it's cell phone, car, laptop battery. It'll flow through that. It'll go to the negative current collector. And then basically you have a looping cycle. And so during the discharge of the battery, you have the lithium ions that are released by the anode transferred to the cathode through that cycle. And then through charging, the lithium ions are released by the cathode and transferred to the anode, so reversed. Again, I have another slide with an annotation that helps kind of highlight that, and maybe hopefully will make a little bit more sense. Okay, so this is for the lead acid battery. This is the chemical makeup, and then I show the annotations kind of showing the producing voltage, the charging of the battery, then the chemistry as well. We can see the spongy lead and then the lead dioxide. Again, many different chemical compositions for these types of batteries, but this is the one that I specifically chose for this project without throwing too much information out there. So the main electrolyte that's used in this is a sulfuric acid, that H2SO4. The positive electrode is going to be a lead oxide, that PbO2. And then we have our negative electrode, which is provided by that sponge lead. It's like a porous lead, if you can imagine, Pb. And then our discharge state, we have that lead sulfate, PbSO4, sulfate SO4 -2 I just have there because I wanted to provide that quick reference there. So again, if you remember that lead sulfate, PbSO4, if we go to charge that battery, we'll release that sulfate back into the sulfuric acid, and then we can ultimately produce our charge again. So you can see there, basically you have around the spongy lead in the top right, You have all the different sulfate um, being surrounded by that, and then producing voltage in the bottom left there, you can see it's going from that PbO2 lead oxide, and it's going through your resistive load, whatever it is, could be a battery, laptop battery, cell phone, anything really. And then when it gets back into that negative electrode, that would be that spongy lead. So now flipping the script here, we got that chemical makeup for the lithium battery. So as you can see, over on the right hand side, I have the parts of the lithium ion battery. So with lead acid, how I mentioned, there can be many different chemical compositions. With lithium ion, I would say there's even more. Um, so for this one, I have my chemical composition, but I wanted to provide in the bottom left a couple different alternatives. Lithium cobalt oxide and graphite, commonly what you're going to see in cell phones and laptop batteries. The lithium manganese oxide is what you're going to see in a lot of hybrid and electric vehicles. And then lithium iron phosphate is what you're going to see in a lot of your solar panels and solar generators. So for this one, um, for the chemical composition that I selected, for the electrolyte, we have that lithium hexafluorophosphate, LiPF6. We have our positive electrode, which is the lithium cobalt oxide, LiCoO2. And then our negative electrode, which is going to be our graphite, which is given by C, Charlie. So with our parts of the lithium ion battery, we have our electrolyte, we have our porous separator, we have our electrolyte, which is going to transfer the ions. We have our anode, which is going to be um, our negative side, and then our cathode, which is going to be our positive. And so in the bottom right there, I show kind of the difference between discharging and charging. So charging is going to be from the left-hand side to the right-hand side, and then that's going to be the cycle. And then for discharging, when the battery is in use, actually pulling amperage or power out of the battery, it's going to be from the right-hand side to the left-hand side. Um, so that's basically the cycle as I described earlier as well. So for this slide, I wanted to provide an actual comparison. So the battery selection that I used, this is a 24 series battery. Basically, it's a size definition, something you would commonly see in a car or maybe an SUV or truck. It's defined as basically the width, height, depth, the physical size of the battery is what the 24 is indicating. So as far as voltage for these batteries and the comparison, they both were about 12.8 volts for output. So on the top, we have the Everstart Max lead acid. That's something you're commonly going to see at like Walmart. That's kind of their store brand. So with the lead acid battery, we have cranking amps. That is how much amps it can provide for 30 seconds at 32 degrees. And for lead acid, we have 700 amps. Cold cranking amps, how many amps it can provide for 30 seconds at 0 degrees Fahrenheit. And for lead acid, we're at 875. And then we go into amp hours and watt hours. That's how many amps the battery at full charge can provide for 1 hour. And then same thing for watt hour. We're just looking at power specifically. Power can be equated to amperage times current. So you're looking at your amp hour times your voltage. And so for watt hours, you can be 617.34 watts for 1 hour at full charge. So now in comparison, lithium ion battery, same size, 24 series group. And for the cranking amps, that's 1020 amps at 32 degrees Fahrenheit for 30 seconds. Cold cranking amps, we're at 480 amps at 0 degrees Fahrenheit. And then we get into our amp hours, and we're at 54 amps for 1 hour. And then our watt hours, we're at 691 amps. So here you really start to see some of the differences between lead acid and lithium ion. So lead acid does have, at cold temperatures, it has a more, like I guess, violent, or maybe violent's not the correct word, but it has a higher amperage output. So when we get into the lithium ion and extreme cold temperatures, you do have a degradation of performance output. However, it's actually a more stable output due to the chemical composition versus lead acid. Lead acid has a higher water content. Um, and again, these are for fully charged batteries. So now when we get into our cranking amps at a 32-degree Fahrenheit temperature, you can see the lithium ion battery has a pretty significant cranking amp output in comparison. So 1020 versus 700 amps. That's directly related to basically the charging and discharging cycles between the lithium, and then just having a higher sustainability because of that cycle. Basically, you have a discharge rate that's significantly different than lead acid. And in the next slide, I'll actually show you kind of a comparison um, based off the discharge percentage between the two. So we'll go to that one next. So on this slide, this is the discharge curve that I was just referring to. So we have lithium ion in red, lead acid in blue. So this is a discharge curve which shows the battery voltage based on the depth of discharge. So as you can see, depth of discharge percentage for the lithium ion is a relatively more sustainable voltage output up until you get to around 87% discharge versus lead acid. It's not quite linear, but you do have a more gradual decline. And so if you look at the percent values at 50% charge, lead acid, you're looking at 50% charge, probably 11.8 volts output versus lithium ion, you're going to sustain the optimal voltage. So if you're in a 12 volt system, you probably need about 12.7, 12.8 volts to indicate full charge. So you're going to be able to sustain that full charge capability versus lead acid. If you have a critical component that operates between, say, 12.8 and 11.8 voltage, you're actually going to not be able to operate once you hit 50% discharge. So this is really where you start to see that chemical composition benefit from lithium ion versus a lead acid. So now we'll start actually looking into some of the temperature effects. So when you think power and electricity, usually extreme cold, extreme heat, bad. So we're going to stay on track with that. And the effects of heat is basically when you have a temperature increase, internally you have a resistance decrease. And then the temperature increase, another way to think of it is that you have a faster chemical reaction rate. So with the resistance decrease, you end up getting a faster reaction rate, which has both pros and cons. And so another effect of heat when you get into the lead acid is that you can have an increased water loss via evaporation or just through that heightened chemical reaction. And so then once you start losing your water, you basically end up slowly starting to depreciate your cycle like rate, the efficiency of it. And then eventually you could negate that battery's electrolyte completely, which would result in needing to replace your battery. You used to be able to service a lot of the batteries. You could add water to them, or you could even buy the electrolyte. As long as your lead plate was still of sufficient thickness and surface area, you could actually service them. Um, that was back kind of in the lead acid, not like nickel cadmium, which we're not going to talk about today, um, but is a lot more common in those types of batteries. Now you're seeing a lot of the sealed lead acids, which are considered non-serviceable. Um, One, the chemical composition, they are more efficient. They give off less heat. They evaporate less, and they're a lot safer, which was the main driver for that big change. So when we get to the effects of the cold temperature, um, when it gets extremely cold, your resistance actually increases, which would reduce your chemical reaction rate. And this also will increase the effort to charge the battery. It'll reduce the capacity of the battery. And then with that increased effort to charge, you now introduce an element of charging at a slower rate. In extreme temperatures, especially with the lead acid, you actually have a risk of the battery freezing, which can basically explode when you introduce a charge. So you really start to get into a pretty dangerous situation. On the right hand side, I have the self-discharge batteries, and here um, each individual line, diagonal line, indicates a different type of battery. So as I mentioned, we're only looking at lead acid and lithium ion, but this graph I thought was extremely helpful. It does show a variety of different chemical compositions. So the sealed lead acid, which, like I said, is a non-serviceable version of the lead acid, you can see that its capacity loss in relation to temperature is actually not too crazy. The big thing with the lead acid is that when you actually increase the temperature and you increase that chemical reaction, you can, to a certain temperature, actually increase the performance of the battery, either the output or the storage capacity of the battery. There are drawbacks of that, which I will highlight later. But I wanted to provide that as a brief overlook. So just getting a little bit more in detail here. So the higher temperature, as I just mentioned, the better performance, higher storage capacity. So Green Tech Renewables did a study, and they found that between 77 degrees Fahrenheit versus 113 degrees Fahrenheit, there's actually a 20% increased capacity in their batteries. The cons of that is that that increased battery capacity actually resulted in an accelerated degradation of the battery. So at 77 degrees Fahrenheit, they were at about 3.3% degradation. When they went to that 113, they saw 6.7% degradation. And so that only gets worse and worse as you cycle the battery more, basically go from full charge to discharge, like to from 100% to zero. You're going to see those degradations rapidly increase. And then um, another major drawback of having extreme heats is that you run the risk of having a thermal runaway, which is basically an exothermic reaction, resulting in the rapid discharge of the battery to where it is um, basically discharging, having a chemical reaction that's producing so much heat that it exceeds the thermal output capacity of the battery itself, like how much heat it can actually dissipate, and it ends up getting into a cycle of overheating, discharging, and basically fully discharges within a matter of seconds or minutes. And it can be an extremely dangerous reaction, even so much that, like in the military or the government, they don't even tell you to try to extinguish it or to try to prevent it. Like if you're on a ship, they literally say throw it overboard. If you're, when I was stationed in Texas, we had to carry a 50-gallon tank, and they said to pick the battery up and drop it in the tank and basically run. It's an extremely dangerous reaction. So heat, batteries, bad. So then on the end of the spectrum, we get to the cold weather. So when we're looking at lead acid batteries, you can actually charge and discharge between 4 degrees Fahrenheit and 122 degrees Fahrenheit. That will vary with different compositions. Same thing with lithium. But the big thing with lithium is that they have a different definition between charging and discharging for temperatures. Charging, they recommend 32 to 113 degrees Fahrenheit, and discharging can be between -4 and 140 degrees Fahrenheit. So with discharging, you have a wider window. However, with charging, you have a narrower window. Again, I have seen extremely different temperatures with different compositions. If you get into like an extreme cold weather element, I've worked with a company Alt E, and they make a lithium ion battery that actually introduces a self-heating element, and they were getting down to like -30 degrees Fahrenheit for their operating temperatures, which is not standard. That battery is also like $8,000. Um, but the charge rate will depend on the temperature, and this will basically be based off of the reduced rate of ion combinations with a lithium ion. And then, as I mentioned a little bit earlier, the forced current rate increase for a lead acid battery. So that'll result in a pressure increase of the lead acid battery as well. So you got to be aware of that. And then the graph that I have here is basically just capacity versus voltage at individual temperature ranges. So as you go from blue to brown, blue being the lowest at -20, brown being 40, you can see that the capacity, um, it even between the high and the low, you're at almost probably 80% capacity reduction based on the temperature. I just have a couple slides left, but I wanted to provide an overview of ways to help maintain and increase or basically sustain your battery efficiency and your performance. So they make items such as maintainers, which will keep the battery charged. It'll be at a reduced amperage rate. Um, and basically it'll slowly charge the battery. There are options to get into fast, smart, or slow charge, but basically you want to try and keep your battery at full charge unless you're in extreme temperatures, extreme hot temperatures, excuse me, then they recommend between 15 and 85% capacity charge. That's due to the increased temperature resulting in increased pressure. They want to make sure that you're in a safe operating condition. You can load test your battery, and that'll be applying a calibrated load for a set duration of time, measuring the battery and how it reacts to a load, and to make sure that it sustains a certain voltage within that measuring parameter. So you also have a conductance test, which will apply low frequency AC current, and then it'll measure the conductance of the battery. That'll indicate your resistance internal to the battery. And then you can usually find out if your porous material, whether it's your separated plate, your lead acid, basically how much substance it has left. And you can indicate the health of your battery. So as I mentioned with the maintainer, you have different charges: slow, smart, and fast. Slow is going to be at an extreme reduced current, and then it'll slowly charge and ramp up your charge status. And so, like the charger that I have, slow charge is like 2 days versus 12. Sorry, slow charge is like 2 days for 12 volts, and then my fast charge is like 3 hours, but it's an extremely higher current rate. But you have reduced heat buildup, and then you have less chance of like that crystallization formation, sulfation that I mentioned earlier. And then smart charger, it'll basically ramp up. It'll start at a low amperage, say maybe 15 amps, and then as your battery capacity increases, it'll slowly start to taper down to a lower charge status. Um, Mine has it. I never really use it, but it basically is like a 50% reduction between the two. And then I've already explained fast charge, but that's just throwing as much current as you can to get a fast charge. A lot of people do that when they need to jumpstart their vehicle, or they need to just get it with enough power so it can start to get the alternator to, start to recharge the system. I wanted to add a note on the bottom, which is basically battery modifications and maintenance is extremely dangerous. If you don't know what you're doing, or you're not familiar with it, consult a professional or just seek a professional to help you. You can also go to places like AutoZone or like one of those parts selling vendors. A lot of them will have testers, battery testers, and they'll actually charge, or not charge you, but they'll test your system for free. And then my last slide here, another way to maintain the battery is to keep it within operating temperatures. And so with that, you can do battery blankets. You can do temperature thermal heaters. That battery blanket basically will have like some sort of heating element in it, and it'll just apply enough heat to get it to that base temperature allowable range. And so you also have, that would be an active one with an electronic circuit internal to it. You also have like a passive version of it for a cold climate, which is basically just a thermal insulator. And it doesn't have a heating element in it. It's basically just a blanket to help keep the heat from the battery inside the battery. And then you have, for a hot climate, you have a thermal insulator that pulls heat from the battery, and just basically tries to pull that heat, reduce it to the atmosphere as much as possible. Um, there's also other capabilities for cooling, which are forced air and conditioned air. Forced air is going to be more of a passive, versus conditioned air is going to be more of an active. Um, there's a lot of this in the electric battery cooling industry. And so the diagrams I have there show kind of the differences between the two. Passive would just be almost airflow going, and you would have that a convection cooling, which is going to be a relatively low heat transfer percentage. And then conditioned air, which are with your active system, is going to be forced air into the battery compartment or the shell of it, and it'll be a lot more efficient. It'll transfer a lot more heat. And then third option is liquid cooling, which is going to be something similar to water or ethylene glycol, which is coolant, basically, as most people refer to it. And it'll go through cooling plates or tubes throughout the battery or around the battery shell, and it'll be forced through with a pump. It'll most likely go through some sort of heat exchanger. Might go through, I mean, depending on how robust the system is, you could even get into evaporators, condensers, to where you have almost like an air conditioned liquid, which is extremely efficient. And you do have some power loss because you have to power that whole system, but it also depends on how much heat you're generating. And the last slide that I have is just the references that I used. So you'll see them in the brackets throughout the presentation. Just followed standard APA format. But I want to provide all these. There's a ton of information out there, and as the industry increases, there's only more and more research and information that develops. So again, I just wanted to provide an overview between some of the differences, the chemical composition, how it may affect you, what you can do to elongate your system. And if you have any questions, please feel free to reach out to me. Um, I do find the topic very interesting. I think it can be beneficial to a lot of people. But thank you for your time, and I will talk to you later.